Welcome, section 5.4, the fundamental theorem of calculus. This is a huge section. I've actually broken it down into two parts. There's three objectives. Today we're only going to study the first one, but this is a very important section. So the first objective is to evaluate a definite integral using the fundamental theorem of calculus. The other two objectives that we'll study in the next screencast are to understand and use the mean value theorem for integrals and to find the average value of a function over a closed interval. But let's focus on the first one. So given an integrable function f of x, an antiderivative of f is often written using the capital letter F. And here's the fundamental theorem of calculus. It comes in two parts. The first part shows that an integration can be reversed by a differentiation. So the derivative of capital F of x is f of x. It can also be written like that. D capital F dx equals f of x. The second part allows to compute definite integrals by using the equation. The integral from a to b of f of x dx is equal to capital F of b minus capital F of a. We're going to use that more than 100 times in the next few months, and I really want you to practice today. Even though I'm showing all the answers, I really need you to grab your calculator now and do the calculations yourself, just to know that you can do it, and that's how you're going to memorize the method too. So the first example is going back to section 5.1 when we were evaluating the area under this curve using rectangles. This function was f of x equals 1 over 8 times negative x cubed plus 7x squared minus 11x plus 21. So if I want to find the exact area under the curve, I can write it like that. The integral from 1 to 5, I distributed 1 over 8, and now I integrate. So the integral of negative 1 over 8 x cubed is negative 1 over 32 x to the 4th power plus 7 over 24 x cubed minus 11 over 16 x squared plus 21 over 8x. Notice the notation here. I've integrated the function, but I haven't yet used 1 and 5, the lower and upper limit, so this is how we write that. Now this is when I want you to grab your calculator and really do it. You need to plug x equals 5 in this expression. So negative 1 over 32 times 5 to the power of 4 plus 7 over 24 times 5 to the power of 3 minus 11 over 16 times 5 squared plus 21 over 8 times 5. And then you subtract the following, which is plugging x equals 1. So negative 1 over 32 times 1 to the power of 4 plus 7 over 24 times 1 cubed minus 11 over 16 times 1 squared plus 21 over 8 times 1. Please pause until you've done it and we'll compare the results. So here's what I got. When I plugged capital F of 5, I got 12.86 and capital F of 1, 2.20. So the definite integral is 12.86 minus 2.20, which is 10.667. As you can see, when we had approximated the area using 16 rectangles in section 5.1, we were not very far from the exact value. By the way, you may have noticed that I didn't write plus c here, and it might surprise you. Well, in fact, when we use definite integral, we don't need the plus c, because when we do capital F of 5 minus capital F of 1, the plus c's are going to cancel out. We have plus c and then minus c, so it cancels out. We don't even need to write them. Second exercise, once again I need you to try it with your calculator, plug in the values just to make sure you know how to do it. the integral from 1 to 3 of x squared minus 3 root x plus 4 dx. First we integrate, and we write the limits of integration here. And now plugging capital F of 3, then plugging x equals 1. Please do it, pause, and come back when you have done it. We get 10.61 minus 2.33, so the integral is 8.274. One more exercise. Using an absolute value. Every time we have absolute values, we have to be very careful. We can't integrate as is. Where is the vertex of this absolute value? It's always when the absolute value is equal to 0. So when is 2x minus 1 equal to 0 at x equals 1/2. This is the graph. So if we want to integrate the function, we will need to break it down into two parts. The first part using this line with a negative slope, and the second part using this line with a positive slope. So here it is. We integrate first from 0 to 1/2, and that's the slope with a negative. That's the line with a negative slope. Then we integrate from 1/2 to 2 with a line that is increasing. So both of these integrals are very easy to integrate, and then we just use the limits of integration, and we find that the integral is 2.5. Given that this was geometrically very easy to do too, we'll just double check. These are two triangles, so the area of a triangle is base times height over 2. For the small one here, the base is 0.5, the height is 1, so the area is 0.25. For the bigger triangle here, base times height over 2 equals 2.25. If we combine these two areas, we get 2.5. That confirms our algebraic calculation here. Find the area of the region between y equals 4 minus x squared and the x-axis for x in the interval 0, 3. This may look like a very easy exercise, but you will have to be very careful when it's given in the textbook or in quizzes and tests. What happens here is that this function 4 minus x squared actually crosses the x-axis at x equal 2. So we have to be very aware of that. I'm not mentioning it here in the question. You have to know that it can happen, and you have to check. So the area is actually the sum of this area and that area, and given that the integral is a signed area, we'll have to be careful, integrate both of these separately. So we need to find where the x-intercept is. The x-intercept is at x equals 2, and we'll integrate both of these areas separately. So the first one here is the integral from 0 to 2 of 4 minus x squared dx. That's the integral is 4x minus 1/3 x cubed. We plug in the limits of integration, and we find that the area is 16 over 3. Now for A2 is minus the integral from 2 to 3 of 4 minus x squared dx. It's the same integral. This time we are going from 2 to 3. And I forgot a negative sign here. Please add it. But the correct answer, I have the negative sign here now. The correct area is 7 over 3. So the total area between the graph of f and the x-axis is a1 plus a2, which is 23 over 3. So that's all for the fundamental theorem of calculus, and in the next screencast we'll study the other two objectives. But what we've seen is that the integral from a to b of f of x dx is capital F of b minus capital F of a, and we saw several examples of that.